welcome you to my lecture today. Those of you online, can you confirm if you are hearing me clearly? Can somebody confirm that?
Yeah.
Oh, okay. Thank you so much. Today, I'm actually going to walk you through uh, what I call moment generating function. I've already uploaded the materials that I call with 4 lecture 4. But 100% of what we're going to do today will be on board. And I need you to all pay attention to what we're going to be doing today. Before I go into moment generating function based on the material that I uploaded, I'll first walk us through the derivation of the mean, the expectation of random variable, you know, I follow negative binomial distribution and Poisson distribution. So let me just, based on the material that I uploaded, okay, today I'm going to start deriving expectation, okay, expectation and variance, okay, of negative binomial, and Poisson distribution. Then after which I'm actually going to, walk you through, introduce you to moment generating function. Okay. After I'm actually, uh, you know, introduce you to moment generating function. So this is what I have for you today, and I need you to focus on the board. Okay. Now, I'll first start with the negative binomial distribution. Okay. So negative binomial distribution. For instance, I have a random variable x that actually follow, you know, negative uh, negative binomial distribution. Let me just say n binom, parameter r and p. So we're basically going to have this x minus 1 this p raised to power r 1 minus p raised to power x minus r, and s star from r plus 1, like that. Of course, this is a negative binomial distribution. We use this distribution to actually figure out the probability of recording a good number of successes, after so many failures. Of course, I've given you example the other time. You can look at when you toss coin several times, okay, and maybe basically you are looking for 4 heads. So the question now is, how many tails am I going to have? Because seeing a tail is a failure. What you have in mind is head. So how many tails am I going to have before I start having a good number of heads? Okay. So this is has a lot of application. I wish I've walked you through the other time. Now, when you take a look at this distribution now, do you know I can ask you to show that this is a PMF, a valid PMF? If you want to show whether this is let me first start with that, showing that it's a valid PMF. Okay, you know, to show, okay, to show that P of X, okay, is a valid PMF. Okay, so because a discrete probability distribution, I actually want to show that S star from R to infinity is equal to 1. Okay, that's exactly what I want to show. Okay. So what I'm basically going to do, if I want to show that, okay, is I'm going to write S star from R to infinity. Okay, this P raised to power R, I can just simply write this guy as Q raised to power that. Okay, I want to show that this guy is basically going to give me 1. So if I want to show that, okay, I can let y be equal to this guy. Okay, if y equal to this guy, okay, so this imply x to be y plus r, right? And if that is taken, so if come, what is going to be, I'm actually going to have this guy here, r minus 1, p raised to power r, this, and y is basically going to start from where? If x equal to r, right, and y equal to this, then y is going to start from 0. Okay, so 0 to infinity. Now p raised to power r is going to come out. I'm actually going to have this guy. Okay, take a look at that. That's what I'm going to have. Okay, so the moment you have that guy now, okay, you actually need to apply a kind of geometric series coupled with Maclaurin or Taylor series expansion. Okay, so what I'm gonna have now is this. If I try to rewrite, I got p raised to power r, okay, y start from 0. I'm actually gonna have this guy, okay, q raised to power 0 plus, okay, y goes to 1. I'm actually going to have this guy, okay, and I'm going to have this guy, okay, and it's going to continue all the way to infinity, okay. So here I'm actually going to have, this is like a 1, okay. We take a look at this guy plus, having this guy, okay. Now, when you take a look at that, okay, so this is more or less, okay, like it's basically gonna be what I have here. Okay, if you want to go by way of binomial expansion, okay, this guy here is the same thing as this guy. Okay, if you expand this is what you're gonna have. Okay, the moment you have that, what is 1 minus q? So here I'm actually having this now, okay, because 1 minus q equal to p, and in the end there's gonna be this, and that is how to show that that's a valid PMF. Okay, so like I said, you can be given any distribution, then can ask you to show that it's a valid PMF. Okay, now we have this for negative binomial. Now, if you have this for negative binomial, for instance, let's say I basically want to, you know, find the mean. Okay, if I want to obtain the expectation, okay, I can use the method of moment. The method we'll be using is called method of moment. Okay, I can use the method of moment generating function that I'm still going to walk you through. Okay, because we say moment generating function, a function that generates moment. Okay, then I can go by way of geometric, generalizing geometric, to get the mean of negative binomial. Okay, so what I want to do now, let's say I actually want to obtain the mean, okay, of negative binomial, okay, because yesterday I've already obtained, when you have a geometric and the probability of x, is actually p, okay, 1 minus p, okay, raised to power x minus 1, and let's start from 1 all the way, okay, don't forget geometric distribution is a special form of negative binomial, and you already know that we derive the mean here, okay, to be 1 over p, okay, the variance here, okay, to be q over p squared, okay. We can use the law of generalization. If I want to obtain the mean and variance for negative binomial, okay, for negative, situation where x equal x1 plus x2 until I get to xn, okay, because the sum of geometric is basically going to be negative binomial. Okay, so when I want to find the expected value of x, okay, right now, here, um, I'm actually talking about negative binomial, because I want to generalize, information that I got about geometric. Okay, of course, yesterday, we've already proved that I'm actually going to have summation expectation of xi. You know that, right? Okay, so what is the expected value of x in geometric is 1 over p. Okay, so if the expected value of that is then another thing is in the case of this guy start from we have x start from r to infinity. Okay, so if this guy is actually expectation of x, which is 1 over p, then we're going to say this summation here, at least to a certain out time, is just basically going to be r, so that we can say this is r divided by p. So r divided by p here is the mean. Okay, so the same way you can also look at the variance, okay, where you actually you're also going to say s star from r to infinity, okay, the variance of xi, okay, the variance of xi is q over p squared, and you can also just put r, okay, by a way of generalization. Now that is all you can so that is all about that guy. Now, the next thing I want to do before I go to moment generated function is Poisson distribution. If there's anyone want to ask question, please, if you get stuck, you let me know, sir. Now, for Poisson distribution, okay, for Poisson distribution, if x follow poi with parameter lambda, okay, the probability of x is exponential raised to power this lambda raised to power x over x factorial, s start from 0, 1, 2, all the way. Of course, the other time I walk you through Poisson distribution, we use it to model real event, event I occur in the blue moon. Okay, so the x here is going to be the numbers of occurrence of that event. Okay, which means the state the state space is going to go from 0 to infinity. And the lambda here is actually the parameter of the distribution. Okay, what if I ask you to show that this is a valid PMF? How are we going to show? Okay, now to show that P of X equal to this is a valid PMF. Oh, those of you online, can you see confirm if you can see the board? The stuff online.
Yes, we can.
Okay, thank you so much. Now, if I want to show that this guy is a valid PMF now, okay, don't forget, because Poisson distribution is a discrete type probability distribution, then I'm also going to do this. I want to show that this guy is going to be equal to 1. What is my x starting from 0 to infinity? Okay, please pay attention to the state space. Okay, so if I want to show that now, okay, I want to show that that's a valid PMF. You know, some of you may be wondering, why are we showing that it's a valid PMF if it is not a valid PMF? Go ahead. Yeah, divided by x factorial. X factorial, yeah. Okay, now, why do we need to show that a function is a probability function? It is the reason why we need to show, of course, every probability function, the totality, the cardinality, the probability has to be equal to 1. That means 100%, right? If it is not, then the expression for mean variance will be wrong. Does that make sense? Okay. Now, I want to show that this guy is a valid. So I'm actually going to have S star from 0 to infinity. What is the distribution of this guy? Okay, I'm summing with respect to x, right? So this guy is going to come out. Okay, that's a constant, right? Okay, then I'm going to have, okay, take a look at that. Now take a look at this guy. Okay, if you want to go by way of Maclaurin series in mathematics, situation where I have something, I'm summing from s, s star from 0 to infinity, and a lambda has a power of s divided by s factorial. Okay, this is the same thing as exponential carry lambda. You know why? Because exponential carry lambda, okay, when you take a look at this guy here, okay, you are talking about lambda 0 0 factorial, lambda 1 1 factorial, lambda 2 2 factorial, and so on like that. So what I have here now, this is a way to write that in short form. Okay, so because of that, so this guy is this guy, right? So what do I have now? Combining them, exponential this and this. What do I have now? When you combine it, that's going to be 1, right? Because this guy is just going to be lambda minus lambda e raised to power 0. That's going to be 1. So that shows that Poisson is a valid PMF. Okay, that shows a valid PMF. Now the next thing that I want to do now is, can we find the mean and the variance of a Poisson distribution? Okay, you want to ask a question? Oh, okay. Now, if I want to find the mean, it's going to be summation s star from 0 to infinity x, probability of x. Don't forget, expectation in a discrete random variable, when you have an x, there's going to be x. In fact, we have a general formula. This is a general formula. We call this guy Hart's moment. We call that Hart's moment. When R equal to 1, that's going to be the mean. Okay, the first moment is when R equal to 1. So when R equal to 1 now, so it means expectation of x. So which is going to be from here to infinity x, the probability of this. Now I'm actually going to have s star from 0 to that. What is the probability? That is the Poisson exponential raised to power this. Look at that. Okay, if I have this guy now, this is a constant, it's going to go out. So I'm actually going to have this guy, okay, s star from 0 to infinity, lambda x divided by x factorial. Now you have to recall that x factorial is the same thing as x into x minus 1 factorial. X factorial is the same thing as x into x minus 1 factorial. And if that is what I have, so if that is what I have, okay, I'm actually going to have expected value of x equal this guy here, okay, summation s star from 0 to infinity, okay, x, lambda raised to power x, then instead of x factorial, I'm actually going to have this guy, okay, So this cancel that. Okay. Now, if this cancel that, I'm actually going to have this guy. Okay. Of course, S is not going to start from 0 anymore. But you know what I want to do? This is carrying S, right? But this is carrying S minus 1. You know the other time when this is carrying X and there's S factorial here and there's a summation starting from 0 to infinity, I was able to say that, okay, this is the same thing as this. If I want to apply that here, because this is carrying S minus 1, I'm going to introduce lambda and lambda raised to power minus 1. Okay, so that, you know, this cancel this, so I'm going to bring this guy out. So I'm basically going to have lambda this. Okay, then I'm going to have combining this now. I have this, then I have this factorial. Take a look at that. This is the same thing as this now. Okay, now even like for instance, let's say if my y equal x minus 1, okay, then y will be starting from 0 to infinity. Okay, if y equal to x minus 1, so in that situation, this guy now, okay, is I can rewrite that guy as this, provided what I have here is what I have here. Okay, so right now this cancel this guy. What do I have? Lambda. So which means the expected value of x in a Poisson distribution is actually lambda. Take a look at that. Okay, if I want to derive the variance, for Poisson distribution, okay, if I want to derive the variance for Poisson distribution, okay, the variance of x is expected value of s squared minus expected value of x all squared. Okay, we've gotten the expected value of x, which is lambda, right? But we need expected value of s squared. Okay, expected value of s squared is the same thing as this. You remember yesterday? Expected value of s squared is the same thing as this. If I want to rewrite the variance now, the variance of s is, by the time you plug in this guy here, so expected value of x into this plus expected value of x minus this guy here. Okay, so which means I need this guy. What is it? Lambda minus lambda squared. Okay, now I need to figure out this guy. I need to figure that guy out. Okay, I need to figure that guy out. Okay, now if I want to figure that guy out, okay, expected value into x minus 1 with the summation s start from 0 to infinity, x into x minus 1, the probability of that. Okay, now when you have that, now you're basically going to have, by the time you plug in the Poisson, okay, you're actually going to have it. Okay, this time around, recall that x factorial can be x into x minus 1. You know, I can keep on going, but I stop here because I wanted this to cancel this guy out. That was the plan. Okay, so here I'm actually this guy is going to come out, right? Then I'm actually going to have x into x minus 1 exponent, lambda raised to power x divided by x into x minus 1, x minus 2 factorial, so that this guy cancels that guy. Okay, you remember what I did the other time? This is carrying x, right? But this is x minus 2. I can just do this, put a negative 2 and put a lambda squared. You see that? Okay. So that's what I'm going to have next. What I'm going to have now. So what I'm going to have now is going to be expectation of x into x minus 1 equal lambda squared this guy. Okay. Then I'm going to have lambda x minus 2 divided by x minus 2 factorial. Okay. And it is x minus 2, okay, factorial. You know that is going to basically going to start from 0 to infinity. Okay. X minus 2 factorial, maybe y, maybe we call it y. The whole of this is what I call that. Okay. So here I'm having this guy now, and this is going to cancel that. So the expectation, okay, is going to be lambda squared. Okay. So this is lambda squared. Then I'm going to come back here, plug that in.